Hello everyone. Let's start today's discussion. Today we are going to move on to a new concept, the concept of the Nyquist plot, and we are going to see how we can use the Nyquist in order to run a stability analysis in our closed loop system. The Nyquist is the continuous kind of like concept of that phasor plot that we already covered when we talk about the frequency response of our closed loop system. Now, we already said that when we have, for example, a negative feedback loop, with a forward path transfer function g and a feedback loop transfer function h, we understand it and we talked about it that the overall transfer function of such a system is going to be the forward pass over 1 plus forward pass time gh. Now, based on this closed loop situation, the closed loop transfer function, we said that what we care about when we talk about the stability is the zeros of the denominator, which means we want to see when this 1 plus gh will be equal to 0, which defines basically the poles of our closed loop system. Now, what Nyquist does is it uses the concept of Cauchy's argument, which is about the contour and how we can plot or transfer a contour and map it to another contour using a function. Okay, now I don't require in this course, or we are not going to discuss about the Cauchy's argument because it's too kind of like mathematical. We are going to just consider that is true, and we just using the characteristics of that mathematical theory. I already posted a video if you're interested to go deeper on a Cauchy's argument and find out where the whole concept of the Nyquist stability came from. You can watch that video and kind of like get more familiar with this argument. Now, and if you want to search it, the argument is Cauchy's argument. If you want to search and learn more about that, you don't need to, just for your own curiosity. Now, this function, when we want to define this condition in the Nyquist discussion, we are going to make it a very kind of like a little bit simplified, and we say, okay, based on this condition which defines the poles of our overall transfer function, we can say these poles happen when gh is going to be equal to -1. Okay, and from the both plot that we saw, the phasor plot that we saw, this -1, we are talking about the complex domain, S domain. This -1 is basically the phasor 1 with a -180 degree. Okay, now you might say that, okay, it's why it's -180, not 180. Okay, this again goes back to the concept of the phasor plot and both plot that we draw. And if you go through the concept again, you are going to see that the phase that we have is going to be decreasing from 0 or a +90 or +180 toward the negative values. So what we are gonna see is actually the phase of minus 180. Okay, now these are what we had before. What is the Nyquist? Nyquist uses the argument, as we said, Cauchy's argument, and say if we have a contour of any kind of like set of points, okay, in an S domain, this is S plane, we can use the transfer function. For example, here, this is transfer function is Ts, okay? We can use that transfer function to map, okay, the same contour, for example, in a T plane. Now, in the text, normally they use f as a function, so just don't get confused over that. Now, based on this condition, we are going to develop a Nyquist method and say the condition of instability in our closed loop system, okay, the condition of instability, let me use another color, the instability in our closed loop function would happen if we have poles in our open loop function that G, okay, in our open loop function in the right half of S plane. We already talked about that. So if we have any poles in the right half side, okay, which basically means the pole have a positive real value, okay, in the complex number, we are going to have an unstable situation. Now, we said that the poles of open loop, which is the poles of this G and basically the GH, actually, these are the same, kind of would have the same poles. If these poles happen to be in a right hand side, okay, that means in the contour resulting from Cauchy's argument, okay, if we have any right hand poles, okay, that means we are gonna have the contour in the T plane circulating over the -1 point. Circulating should be clockwise. Circulating clockwise around the point -1. Again, you can read the Cauchy argument. I don't want to discuss all the mathematics behind it, it's too long. But what it says is that if we have any right half pole in our open loop circuit, based on the closed loop poles condition, the contour that we have here, okay, would encirculate the point -1 in a clockwise manner. So consider that as a characteristics of the Cauchy's argument, and we are going to accept that. Now, we are gonna define the stability of our closed loop system based on those characteristics as z equal to p plus n when z is the number of zeros of closed loop system in right half plane, the right half of our S domain. The P is the number of poles in open loop, the number of the poles in open loop system that are in the, again, right half of our estimate plot, and the n is the number of in circlements. Remember, it's clockwise. Around point -1 plus j0, which is that -1 on the real axis. Now, what happened? If we have poles, okay, if we have poles in our open loop in right half side, okay, we are going to have, based on what we discussed here on the contour part, we are going to have some encirculating in our closed loop contour. Now, if those encirclements happen around -1, okay, and they are not equal, the P plus N summation of open loop right half poles and the encirclement, clockwise encirclement around -1, if they are not canceling each other out, so we would resulted in a number of the zeros of our closed loop in right hand side, then our system is unstable. Let me rephrase that. In any system, we are going to have, in TS, we are going to have some zeros and poles. If it happened that zeros or poles happen in the zeros of our closed loop happen to be in a right hand side. So if we have some zeros, let's say this is T of S, closed loop basically, system. If we have zeros here, okay, and in our open loop, we have poles also in the right hand side, okay. In this example, we have 1 0 in the right hand side and 1 pole in the right hand side. When we draw the contour, when we map the contour in the T-plane, okay, since we have 1 and 1 here, 1 and 1 here, if 1 here, 1 here, if we see any number of encirclements around -1, we are unstable, because then this equation is not met. In this example, here we have 1 equal to 1 plus n. If n is not 0, then this equation would not happen. So we are not stable. Is that clear? If we don't have any zeros in the right half plane, that means these p and n should cancel each other out. Okay? Any question about that so far? This is basically the definitions of the Nyquist concept. Any question? Now, we said we want to map our open loop system, the poles and zeros in open loop system, using the transfer function into another map, which we call it the T-plane. Okay? Now, we only care, as you can see, we only care about the zeros and poles in a right half side of our plane. So that means we can simplify these contour mapping, and we can only consider the contours that include the right half side of our S-domain plane. Is that clear what I said? We only care about the zeros in right half side and the poles in right half side to consider the stability. That means instead of having a contour all around the place in S domain that encapsulate all those zeros and poles, we can only focus on what's happening in the right hand side, because that's all we need for that equation. So if that is true, we can define the contour mapping for our Nyquist as mapping, this is S-plane, mapping the contours that encapsulate everything in the right half side, so from minus infinity to plus infinity in imaginary line, all the way to plus infinity, okay, in our real. This R is equal to infinity. So that contour here encapsulate all the right half side of our system. Is that good? Now, we already know what are the zeros and poles of our open loop and closed loop circuit. We can find them based on the transfer function. Okay? The only thing that we have to see is what's going to happen when we map this contour using the transfer function of our system in the T-plane, and what would be if would that contour, the mapped contour, would encircle the point -1, and how many times it would encircle that, so we can analyze this equation to see if the condition is met or not. Is that clear what I said? Are we good? So, basically, I am gonna kind of like draw a very general kind of like contour. Let's say we map that contour using the TS, and we are gonna end up in like such a contour that the -1 is here. Okay, and this is, let's say, still clockwise. Then here we encirculate the point -1 one time clockwise. Now, if it happened to have another encirclement counterclockwise around that, okay, that would consider a minus number of encirclements, the counterclockwise. So one clockwise, one counterclockwise, they would cancel each other out, and the n is going to be 0. Very good. So this is how you can count the n. The condition is clockwise encirclement. So if you have counterclockwise, you should subtract it from the number of clockwise. Now, let's do an example and see how these concept means, and be kind of like more clear about what's happened. Now, in this example, I also want to show you a step by a step of drawing or mapping the Nyquist contour in S domain into the contour in a T domain. So we have S domain, the contour that we have is this. We have some critical point in the contour that we need to consider when we wanted to like map that. One is here, one is here, and one is here. These are the critical points. If we can understand what happened to those points, we can estimate the mapped contour on the T domain. So we are going to call it A, B, C, and D. Now in this example, GH is going to be 10 over S plus 1 times S plus 2. Now, look at the open loop function. The poles of our function are -1 and -2. Correct? Is that good? So, that means the P that we define as a number of poles in an open loop circuit at the right hand side is 0. Are we good so far? We don't have any pole in this example on the right hand side of S domain, so this is 0. Now, we are gonna try to map the contour now into the T domain using the concept of basically polar plot and the Archie argument that we mentioned. So let me draw the T domain. This is going to be our T plane. If our function is 10 over S plus 1, S plus 2, and we wanted to consider the frequency response, then that means the S is going to be equal to J omega. Are we good? That was the concept of phasor plot that we talked about. So if S is J omega, that means our GH is going to be 10 over J omega plus 1 times j omega plus 2. Are we good? Now, we already said that we can show this gh as a phasor, magnitude, and a theta. Correct? So, let's find out what would be the representation of this function in a phasor domain. So, for each omega, what would be the magnitude of the phasor of gh, and what would be the phase of that phasor gh. Now, this one, if we consider it as the complex number, and we wanted to like show the phasor of that, it is gonna be the square root of omega square plus 1. You know how to calculate the magnitude of a complex number? Are we good on that? It's a triangular concept. Any question what I did? We have j omega plus 1. The vector that shows this place, this complex number, the magnitude of that is going to be the square root of omega squared plus 1 squared. What about the theta of that? The theta of that, sorry? Tangent inverse, okay? The tangent inverse of x over r. Imaginary part over the real part. You remember that? So the theta is the tangent of that value. So it's going to be minus, no, this is still the tangent of tangent inverse of omega. Are we good so far? Are we good? Now, what about the next vector here? J omega plus 2. Again, it's going to be omega squared plus 4 as a magnitude. And same concept, it's going to be tangent inverse of omega over 2 as imaginary over real part. Are we good? Now, we have the numerator and denominator in a phasor system. What would be the value of our function? This is going to be omega squared plus 1 times the square root of omega squared plus 4. This is going to be our magnitude, and the phase, they are going to add to each other. So it's going to be Tj inverse of omega plus Tj inverse of omega over 2. Now we have 10 with a 0 degree at the denominator, so the overall vector of gh is going to be 10 over that amplitude okay, and the phase is going to be 0 minus this, which means it's minus Tj inverse of omega minus Tj inverse of omega 2. So far, we just plot our system in a phasor domain. Correct? Now, when we talk about the point A, which is in the origin, what is the omega at point A? This is in origin. What is omega at point A? Here, S is equal to j omega, so we are only on this real axis, the imaginary axis. What is the omega on A? Zero. This is 0 plus j0, right? So omega is 0. So if we want to map A to the t-plane, we have to put omega as 0. Are we good? So if you put omega as 0, you are going to have, so if omega is 0, then that phasor, let's say m theta, is going to be 5 with a 0 degree. This is 0, this is 0, is going to be 0. Okay? And if you put zeros here, this is going to be 1, this is going to be 2, so it's 10 over 2. Are we good? So, 5 with a 0 degree. Where is going to happen in the t domain? 1, 2, 3, 4, 5. And we have 0 degree, so it would happen in real axis. So the mapping A to the t-plane would end up here. Let's call it A prime. Are we good?
Wait, how did you go find?
A is omega equal to 0. So we put omega equal to 0 in the phasor that we find for our GH. Okay? If you put 0 in this function, this is tangent inverse of 0 minus tangent inverse of 0, which basically means 0. Okay? So the phase is 0, phase of result. If you put 0 in amplitude, this one become 1, this one become 2. Okay, so it's there's multiplication 2, 10 over 2. Okay, so this is A part. Now, what about the B? What is omega at B? What is omega at B? It's plus infinity. Is that clear? It's plus infinity. So if it's plus infinity, we put here, if omega goes to plus infinity, okay, this is going to be infinity, this first term. Second term is also infinity, so the denominator is basically infinity. Are we good? 10 over infinity is 0. So our m theta here is going to be 0, the amplitude. What about the phase? Phase of tj infinity is going to be 90. Are we good? This is the tangent. This is the tangent function. This is 90. This is minus 90, and this is 0. This is a tangent function. So tangent goes to infinity when the degree is 90. Are we good? So this one becomes 90, which is it has a minus sign in front of it, so it's minus 90. This one is also going to be infinity over 2, which is infinity. So again, it's going to be minus 90. So minus 90 is going to be minus 180. Are we good?
Good question. For W goes to 0, you got a magnitude of 5.
Yeah.
Shouldn't it be 10 over 4?
No, it's the square root. The square root of 4 is 2.
Oh, yeah, yeah.
Yeah? Okay,
You're
so
right.
2 times 1 and 10 over 2. So it's gonna be 0 with a minus 180. What that means? That means it's here, B prime is here. Now, it has minus 180. That means when we approaching B prime, the vector should be on the negative side, minus 180. Am I clear? Omega that approaches very near B and approaches the B prime, the vector is here. Correct? That vector is basically we can approximate that vector is the same vector of B prime because it's infinite a small distance of B prime. That means the trajectory of AB should be curved and go back to the. Hey, is that clear? What happened? No? What? We are gonna go, this is A to B. We find the A prime place, we find the B prime place, so our contour is gonna go from A prime to B prime. That's clear? Now, B prime has a minus 80 degree. Okay? If we have a point, that means if we have a point very close, let's say this is B double prime, and it is very close to the B prime when the distance between them goes to 0. Infinite small distance between B double prime and B prime. So if this is that close in the trajectory of our contour, that means the both vector that shows B prime and B double prime should have the same phase. Do you remember when we talked about the Lucas, the concept of the departure degree, the degree of departure from a pole? We said we consider a very close pole to our original pole, and because they are infinitely close to each other, the degree of both of them should be the same, approximately. Is that clear so far? So if the degree of B double prime is going to be the same as the degree of B prime, so the theta of these two are going to be the same, that means this infinitely close B double prime should have a vector from origin with a theta of minus 180. Okay? That means this, when we arriving this B prime, we are gonna see minus 180 as our theta. Are we good? So this contour should approach B prime with a degree of minus 180. Knowing that, we can plot this. Now, let's talk about why we had this curve. We consider 0 and infinity for A and B. Now, if omega goes from 0, we increase the omega from 0, okay, but we don't reach infinity, like omega equal to 100 or 1000, okay? What's going to happen here is the denominator is going to increase. Are we good? So the magnitude will decrease. Is that clear? What about the theta? The theta of that function, okay? The theta of that function, if we go higher from 0 to infinity, it is going to be somewhere between 0 and 90. Are we good? So we are going to have for both argument, for both terms, tangent omega and tangent inverse omega and tangent inverse omega 2. So the theta would go from 0 to 90. They have minus sign, so it goes from, and there are two terms, so it goes from 0 toward minus 180. Are we good? So all the vectors that connect and follows this path should go from 0 degree, theta 1, theta 2, theta 3, this is the whole theta, okay? Should decrease from 0 to minus 180. So we know that the trajectory is in the bottom half of our system. Is that clear for the theta? Now, let's look at again in the amplitude. We said if omega increase, we are going to have lower amplitude. But omega starts from 0, goes all the way to infinity. Omega squared increase if the value of omega is 1 or bigger than 1. When omega is between 0 and 1, what's going to happen? Omega squared is actually decreasing. Is that clear? Are we good? So it is gonna be slightly bigger than the initial condition, but as we approach, when we have, like, for example 0.01, we are still at value of 5. If we go to 0.1, okay, the denominator would have a slight increase, okay? So when omega is less than 1, the decrease is slower. The increase of the denominator, which means the decrease of amplitude, is slower. Is that clear? But if it goes toward from 1 to plus infinity, now the speed is going to increase. If omega is 1, we are going to have a square root of 2 times the square root of 5, okay, which is 1.4 times 2.1 to, it is going to be 4.9 or something. Okay? And the tangent is going to be, this is 1, so its tangent of the 1 is going to be 45 degree, and the tangent of 1 over 2 is going to be 60 degree. So we can map that with a theta of minus 105. Is that clear what I'm talking? So if we approach, we can have some sample value for omega and find how we approaching, how the contour goes from A to B prime, A prime to B prime. Is that clear? Now, so far we only covered this part of the system. What happened when we go from B to C to D? Again, we are gonna consider omegas that describes those values of B, C, and D. Now, those values are in infinity. So we can just put infinity in our system and find out what's going to happen. So what we are going to do is we are going to put S or omega, let's say S, equal to the limit of R e to the power of j theta, which is how we can show a complex number when R goes to infinity. If R goes to infinity, okay, the theta here, the JH of that S is going to become the limit of 10 over R e to the power of j theta plus 1 R e to the power of j theta plus 2. I just put the S equal to R e to the power of j theta on my function. Now, this is equal to the limit of 10. You can multiply these two. R goes to infinity. This 1 and 2 would not affect anything. So it is going to be R squared e to the power of j 2 theta. Are we good? Are we good what I did? We want to consider B, C, and D. We can show B as a complex number or a phasor or a vector when the R goes to infinity. When the amplitude of that vector goes to infinity. Now, that vector is R e to the power of j theta. Same, it is the Euler representation of that phasor that we had. Are we good? Now if R goes to infinity, this 1 and 2 would not affect anything. So we have R ej theta and R ej theta multiplying to each other. So we are going to have R squared ej 2 theta. Are we good? Now, at point B, what is the theta? Theta of point B? What is the theta of point B? 9. So if we wanted to show point B, the theta of that is going to be e to the power of 90, which is it's 2 theta, which is 1/8, right? And it's in the denominator, so it's become 0 minus 1/8. So here we are going to have theta equal to 90. That means 2 theta is This is minus, oh sorry, that means 2 theta is 180. That means the overall function in point B is going to be minus 180. So the theta of B prime is going to be minus 180. Are we good? What about C? What is the theta of C? Theta of C is 0. 2 times 0 is still 0. And when you put that in here, we have a 0 degree in the denominator, 0 degree in denominator, so the theta of C prime would be 0. Are we good? So same kind of like concept. Now, based on the same concept, theta of C prime is going to be 0. What about the theta of D prime? Now, D is in minus infinity. The degree is minus 90. Okay? We put minus 90 here, which become minus 180. It's in denominator, so 0 minus minus 180. That means the theta of D prime is going to be 180. Okay? What about their magnitude? When r goes to infinity. What happened to their magnitude? The magnitude is 10 over r squared. If r goes to infinity, their magnitude, all of them, is going to be 0. Are we good? Is that clear? So, what's going to happen is B prime is going to be 0 minus 180, which actually is consistent with what we find when we wanted to like draw the A prime to B prime. So B prime is here. C prime is 0 with a 0 degree. So it is still here. C prime is still here. And D prime is 0 with plus 180. So it is still here. Where should I? D prime is still here, but with plus 180. What that means, plus 180? That means when it wanna leave the D, okay, do you remember again the departure angle? When it wanna leave the D, it should be touching the real axis with 180 degree. Are we good? And we already know the A prime. So what's going to happen is we are going to have the same trajectory between the D prime and A prime. Is that clear what we did? Are we good on what we did?
So if it leaves the D at 180.
That means the trajectory when leaving 180, it should touch the real axis with 180 degree. So this is 180 degree, right? Right? So it should touch the real axis and then leave. Now, one thing, the same characteristics that Nyquist had, whatever contour you have, it is symmetric, okay, in respect to the real axis. So eventually, if you find the A to B prime here, you should see the mirror of that when we wanted to like find the D prime to A prime. Same goes here. If you find the B prime to C prime, it should mirror the C prime to D prime. Now in our example, C, B, and D would be mapped on the origin in T domain, so it is intrinsically kind of like symmetric. Is that clear what happened? Now, let's talk about, let's talk about the stability analysis. What was our condition? What was our condition? We want to see if number of the zeros is equal to the number of the pole plus number of the encirclement over minus 1. This is minus 1. Our pole in the right hand side for this function, the number of the poles on right hand side was 0, correct? Are we good? So this number here is 0. Look at this. How many zeros we have in the right hand side? 0. We don't have any zeros. So this one is also 0. So if we want to have a stable system, the number of the encirclements around the minus 1 clockwise should be 0. Now look at the Nyquist. We don't have any encirclement around minus 1. Correct? So this is also 0. So we meet the condition of this equation. So this system is a stable. Is that clear? Are we good on that? Now, let me fastly go over another example, because I wanted to make it very clear. What's happened in our Nyquist. So the concept behind it, you don't need to memorize that, just understand it to see what's happening. The new GH is gonna be S plus 2 over S plus 1 S minus 1. So in estimate, what are gonna be our poles and zeros? We are going to have a 0 at minus 2, a pole at minus 1, and another pole at 1. Are we good? Now, so here our P is 1, okay, and our Z is 0. Are we good so far? Now, we wanted to map this contour A, B, C, and D into the T domain. In A, let's first find out what's going to happen in our system. So GH in J omega is going to be J omega plus 2 over J omega plus 1 times J omega minus 1, which means in a phasor system, the amplitude of these are going to be a square root of omega squared plus 4 over, this is the square root of omega plus 1, again, a square root of omega plus 1, which means omega squared plus 1. Is that clear? These two amplitudes are the same. It's a square root, so it's just, we can get rid of the square root. It's going to be omega squared plus 1. And the phase is going to be the Tj inverse of our denominator, our nominator, minus the Tj inverse of this omega minus this one is minus 1 over omega, so it's going to be 180 minus Tj of omega. So, and there's a minus in front of it, minus 180 plus Tj inverse of omega. So these two cancel each other out, so we are going to end up in Tj minus omega over 2 minus 180. Are we good? Now, for A, the omega is 0. If omega is 0, it's the square root of 4 over 1, which is 2. So we are going to have 1, 2 here. And the vector is Tj inverse of 0, which is 0. Okay, minus 180, which is minus 180 which is which overall in A prime we are going to have 2 minus 180. Where is this point? 2 with a degree of minus 180 is going to happen in a left hand side on the point 2. So this is going to be our A prime. Is that clear what happened? We put zeros here. This becomes 2 over 1. This becomes 0 minus 180, which is minus 180. That means we have a vector with an amplitude of 2. Okay? The vector with an amplitude of 2 and minus 180 degree. Are we good? So this is going to be our A prime. The B prime, omega is infinity. If it's infinity, you have to, infinity over infinity don't work. You have to make a differential from that function and then put it to infinity. I'm not going to go through that differential. You know that, right? When you have omega over omega, when you have infinity over infinity, whatever function you have to take derivative and then limit the omega to infinity. Whatever happens is going to be the result. Is that, do you remember that from calculus or something? Now, for B prime, if you put the omega to infinity and solve that, the amplitude is going to be 0. The degree is 90 minus 180, which means minus 90. So it's going to be 0. It's going to be 0, okay, with minus 9. So it's going to be touching here. So we are going to have such a movement. Now, for C prime and D prime, we said we are going to have the limit of, I'm going to do the function itself. So it's going to be r e to the power of j theta plus 2, r ej theta plus 1 times r ej theta minus 1. These constant number and r goes to infinity. These constant number doesn't matter, so it's going to be r over r squared ej theta ej2 theta, which means 1 over r e minus j theta. Are we good? You know what happened here, right? Is that clear? So, put the r equal to 0 to infinity, all the amplitude for the c prime and d prime, if it goes to infinity, is going to be 0. Are we good? What about the thetas? The theta of c, the theta of c is 0. Are we good? So c prime is going to be minus theta, which is 0 again. What about d? D is minus 90. The theta was minus theta, so it's become plus 90. So both, all those b prime, c prime, and d prime would happen here. So b prime, c prime, and d prime would happen at origin. We already know b prime has minus 90, d prime has plus 90. That means it touches the positive imaginary line and goes back to the a prime. Are we good? And now how it goes back, you can have some sample point, or you can actually watch the formula. Okay, this formula has a certain kind of like a graph on it. So you actually can find what's happened if omega goes from 0 to infinity. Is that clear? Now, this is our Nyquist. We have our P, we have our Z. What is our N? N was the number of the clockwise encirclement over -1 point, right? How many clockwise encirclement we have? We said the number of the encirclement, clockwise encirclement, is whatever number of the clockwise circle that we have minus clockwise circle that we have. Is a net clockwise number of encirclement for point -1. How many we have on that Nyquist graph? What is the n? Come on, it's very simple. Please, one person answer me. How many n we have? Net clockwise number of encirclement around -1. Clockwise. Negative 1. Correct? N is -1. Our condition was z equal to p plus n. Z is 0, P is 1, N is -1. The condition is met. That system is a stable. Are we good? Is that clear what happened? How we draw the how we draw the Nyquist graph and how we analyze the stability. Any question? No? Okay. Okay, if you don't have any question, this is it for today. So we are gonna end our session here, and in next session we are gonna talk about some special cases in the Nyquist parts.